well found or not. Okay, so the reason I'm asking this question is that from academia we have to ask ourselves self-doubting question, so that because the industry will go its own way, but in academia we have to ask this question because we want to see whether we are going on the right track or not, because we are not neither involved with the government nor with the industry, right? So we should be like following the truth that is there, right? So what we see now is that we see a lot of interest in EV. So let's see whether that interest is well founded or not. So if you just to start with, so what happens is that in our present day scenario, our fossil fuel car, our normal cars, so we fill up our tank, we move around. So we deplete our petrol, then we go back again, fill the tank, again move around, right? So similarly in EV also same thing happens. There is a battery. Instead of petrol, there is a battery. So this battery, we charge it, then we move around, battery discharges, again we go back and charge it. So this is exactly where the problem comes into picture, right? So from an external perspective, when you are filling up the tank, you go to the filling station, it takes hardly 2 minutes. If there is space, then hardly 2 minutes to fill up your tank. But the same thing is not true for an EV. Like the charging actually takes a longer time. So that is what makes uh, popularizing EV to the general public, right? So that is one of the things that people always think about, whether I should buy a EV or not, right? So this is the general trend. That so this slide is basically telling you what is the difference between a IC vehicle and a EV is. Now, like if you ask a general person who has no um, technical appreciation for EV and things of that nature. So if you ask them, like my mom, if you ask her whether I should buy a EV, the first question she will ask is how much money I will save. So that is actually pretty easy to calculate. So a normal car, let's say 20 kilometer per liter, 100 like rupees per liter. So 5 rupees per kilometer will be your cost. So per kilometer you are spending 5 rupees. For EV, if you look at the above table, this table is always provided by the manufacturer. So the EV has an onboard charger. Okay, so that charger like has a certain capacity, like 6.6 kilowatt in this particular case, right? So that might be 3.3 kilowatt, it may be 7.2 kilowatt, whatever the onboard charger capacity is. Now, there is a battery rating for that EV, that is 30 kilowatt, right? So what it basically is saying is that per hour of charging, like per hour of charging, that means if I charge the battery with 6 point with the onboard charger for 1 hour, I will actually be spending 6.6 kilowatt hour of energy. So in order to charge the complete battery, I will require about 5 hours, because I require 30 kilowatt hour, right? 30 kilowatt divided by 6.6 will be telling you the number of hours that will be required to charge the battery. Now, per hour of charging, actually you are actually putting about 107 miles. So with 6.6 kilowatt hour, you are putting with 30 kilowatt hour, you are putting about 107 miles. So from there, you can actually back calculate how much per kilometer you will be spending. So it is in miles, but so I have converted into kilometers here. So basically what is happening is that sorry, with 5 rupees per unit, you can see that it is 6.6 kilowatt times say like 7, about around 7 units, let's say. So 46 rupees for 37 kilometers. 37 kilometers is this per hour thing, right? So the per kilometer you are actually spending one rupees 25 paisa. So where normal car is you are spending 5 rupees per kilometer, for an EV you are spending 1 rupee 25 paisa, but that is under the assumption that it is 5 rupees per unit. But normally it is not 5, it may be 7. Then you know how to calculate this this whole thing now. All right. So what that means is that no matter what, we will actually have some benefit to the spending, like per kilometer price will be much better for a EV compared to a normal car. Environment things aside, this is the monetary part of it, right? So now, if you look at what is inside an EV, okay, so what happens is that if you look at, see, in a normal car, there is a IC engine, and that IC engine is rotating this way. But in EV, actually, there is a battery, and then there is a inverter. There is an inverter that is there. So battery is basically feeding to that inverter, and that inverter is feeding to a PMSM motor, and that motor is actually taking care of the wheel, right? So now this is the powertrain for an EV. Okay, so instead of IC engine, we now have a battery and then an inverter and a PMSM motor. So as we move around, then what happens is that we discharge the battery. So when we discharge the battery, we basically have to charge the battery. So that battery can be charged in two ways. The first one is if you go for a onboard charging, that means at home, if we are charging, we actually use a single phase AC supply. So that AC supply is converted to DC through this onboard charger, and then that goes to the battery. Okay, obviously the onboard charger, as it is on board, that means as it is inside the electric vehicle, so therefore the size of this charger will be kind of smaller. It is limited, right, in size. So it takes a longer time to charge a battery through a onboard charger. But ultimately, we have a AC power. We have to convert it into DC power, because DC power is what the battery power is, right? So either it can be converted through the onboard charger, or we can directly actually give a DC. So if we are giving directly a DC, then we use the two terminal of the DC, and then we directly charge the battery. So if you directly charge the battery, all you are doing is this onboard charger, which is inside the vehicle, which has a limited size. If you can move it outside the vehicle, then we can have a bigger size, right? Because we don't that the charger need not be moved around with the vehicle. So therefore, it is a static charger. It can be of any size. So that size, it is a bigger size. So that's why it's called a fast charger. It is directly converting the AC power into DC and directly giving it to the battery, rather than the onboard charger, which takes a AC and convert it into a DC, right? So, and there are certain numbers I have written here. These numbers are from the internet, so it is absolutely, there's nothing, I mean, I have not made up anything here. There's whatever is available on the internet, I'm basically saying. But what is very important to know here is that, like, how much electrical engineering is used in an EV. Okay, that is what makes it very, very interesting for people like you and me, because we are actually from electrical engineering. So either you think about a battery, or you think about an inverter, or you think about a PMSM motor, or you think about the onboard charger. So they are all electrical engineering circuits, which are predominantly used in electric vehicles. So another reason why you should learn about electric vehicle is that tomorrow, let's say, electric vehicle market becomes saturated. So that actually will not affect anything, because then people will think about electric aircraft. So the same thing will again be there, right? So once you learn about electric vehicle and what are the advantages and disadvantages of it, then that the same thing will be applicable to other fields as well. All right. So so let's go forward. So the narrative that is being used to popularize electric vehicle is that we have it's an environmental thing, like it is environmentally less polluting, right? But that actually is not that correct reason. The reason is that because see, at the end of the day, the battery has to be charged, right? And the battery has to be charged with grid power. So whether the grid power that you are generating is green or not also matters, right? So most of the time, if you are using coal-based, right, thermal energy, then that is not clean anymore, right? Because you have basically replaced this fuel like petrol with burning of coal, right? So therefore that can be a weird reason. So therefore, if it is not, if the energy that you are generating to charge a battery is not coming from a green source, then that reasoning actually is flunked, right? So and that is most of the time the case. But one thing good that happens with electric vehicle is that in a place like Delhi or in a place like a bigger city where there are many vehicles. So if there is electric vehicle, the pollution is less here, right? But the pollution has been transferred to the wherever the energy is being generated, right? The energy is generated in some coal power plant, and the pollution has been shifted from Delhi to that place. But overall, like environment-wise, the pollution probably is the same, but it is less it is more easier for us to control the pollution in a centralized place than with electric way with cars, right? So that is one of the advantages that is cited. Okay, and that actually works. I think when I move around in Delhi, I see that this, because of electric vehicle, the pollution here is less, but that has been transferred somewhere. But that is a good thing, because the concentration of population is more here in Delhi, right? So, or in any bigger city. But when the West, okay, the collective West that we call, is popularizing certain technology, there is a narrative that is being made, in this case green narrative, and there is an actual reason why electric vehicle is promoted now. All right. So the actual reason why electric vehicle is promoted now is because there are two technologies that have improved. Like if you go back to the question that I was having, that electric vehicle was there, but why it didn't become popular? The reason it didn't become popular is, at that time the battery technology was not good, and at that time the power electronics technology was also not good. So now that those two problems have been taken care, all right. So the battery technology has become very nice, and the power electronics technology also has improved significantly. All right. So these two like technological innovation in these two fields have actually given rise to a renewed interest in electric vehicles, even though the normal narrative that is made is that it is environmental friendly, etc. But that's fine. But it would have been environmental friendly that time as well, right? Why didn't they take it up? Because now it is more viable to do that. So that is why it has become more important now, right? So far, is there any question, or should I go ahead? I cannot see the participant, so if you have any questions, please let me know. Right. So now, if you look at the battery technology comparison, so in the previous case, in 1976, people used to use lead acid battery, but now they have started using lithium ion battery, right? So the lithium ion battery enjoys a lot of advantages, okay, compared to lead acid battery. So lithium ion battery, so what the advantage, the major advantage they have is the energy density. Okay, so the energy that can be stored in a small package is far higher compared to lead acid battery, and that is kind of obvious, because if you look at the cell phone that you are having, so cell phone actually runs pretty nicely, right? So that is actually, even though we watch movies, we talk a lot, we take a lot of videos, still we like the battery will last for a day or maybe sometimes more than a day, etc. So clearly we can see that lithium-ion battery has advantage in energy storage. Right. So the second important advantage of lithium-ion battery is the depth of discharge. So lithium-ion battery can be discharged pretty pretty low, right? So up to 10%, even 5%, you can discharge it compared to lead acid battery, where if you periodically discharge a battery to 10 or 5%, then the battery ages fast. That means you have to change the battery more often. And that is also kind of obvious if you think about the inverter that you are having. Okay, in your home, you are having a home inverter. So if there is frequent power cut in your locality, then you can see that you have to replace the battery more often. Okay, but the same is not true for the cell phone, right? Where even though I mean, we actually discharge the battery to 5%, still it will turn on. I mean, still we can charge it and use it as we wish, and it lasts for about 2-3 years, very easy, right? So therefore, this depth of discharge is a very important advantage that lithium-ion battery enjoys with respect to lead acid battery. Then third one is the durability of the battery. Lithium-ion battery lasts longer, which is kind of obvious with your cell phone as well, right? And cycle life. So number of charge discharge is more. Like every day we charge and discharge our cell phone battery, still we are yeah. So Shekhar, I'm going through the same slide, right? Battery technology slide, right? So durability. I'm one by one. I'm just going through them. All right, and then cycle life. So cycle life in number of charge and discharge is kind of more. And another one of the most important thing that lithium-ion battery enjoys is that it can be charged very fast, like 2C or 3C type of charging. That means like we can charge the battery in a fraction of time compared to a lead acid battery. Let's say, for example, if we have a 100 kilowatt hour battery, let's say I'm just giving an example, right? So 100 kilowatt hour battery. So if we charge a lithium-ion battery with 200 kilowatt hour, we will charge the whole battery in half an hour, right? 30 minutes. But lead acid battery cannot even do that, because lead acid battery you have to charge at, let's say, 0.5 or 0.6 of the SOC. That means you can only go until 50 kilowatt charging. That means it will take 4 hours. So a 100 kilowatt battery can be very easily charged in 30 minutes. Okay, but a lead acid battery of same size will take like 3 or 4 times that time. So this is the charging time. So, and that is of importance to us, because this is what we are trying to make. We are actually trying to make the charger. Okay. So if you have any questions so far, Shekhar, you had a concern about the slide not moving. Hope it is okay now, because I was on the same slide. I was just explaining each and everything, right? So if you have any questions, just type it in and I will answer.
So basic reason is manufacturing only. It's material.
So basic, see, reason material wise, see, it is actually worse in case of material. Well, lithium is not in our country. Now we have to kind of import it and things like that. And lithium, once it is done, what do you do with that lithium? That is also a big concern. Compared to that, lead acid is far easier, because you just if in your home also we just put distilled water and it just runs for a few more time. So material wise, maybe lithium ion may be bad, but it enjoys a lot of good things like energy density. That means in a small space you can actually pack a lot of energy. Okay, so therefore it can move like 200 kilometers you can have in the same a car will have a like battery underneath completely, and you can go for 200 kilometers and so. And also the advantage that lithium ion has is that that it can be charged pretty fast. compared to a lead acid battery. Is that?
My question was the reason for slow charging in lead acid due to material manufacturing only. No? That is
Material manufacturing, yes, yes. It is like the material doesn't allow fast charging.
Yes, okay.
Right, correct. So actually I'm not a battery expert, so but this is the electrical things that I know about. That's what I'm sharing. Anyway, so next one is power electronics. So power electronics, if you follow power electronics, how it has moved from 1957 till now, you can see that power electronics is actually the story of switches. Okay, switch is the story here. So if you remember, when we were taking our undergraduate power electronic course, we were taught about SCRs and thyristors and things like that, and no longer they are used. Actually, there are very few places where thyristors and SCRs are used. I mean, they are having a comeback in some inverter scenario, but still I will say that SCRs and thyristors have I mean, compared to MOSFETs and IGBTs, they share a smaller market share, right? Now, but what has happened is that we have actually gone to MOSFETs, even higher voltage MOSFETs, IGBTs, and now we are in the WBG technology, that means wide band gap technology, which is like silicon carbide or GaN devices. So all these switches actually have improved the converter design. That means the same rating converter, let's say 1 kilowatt converter you want to make. Previously, the size used to be big because the switching technology was not good. Right now, with WBG technology and other even silicon technology, the size can be made very small. So that is one of the advantage of power electronics switches. So that has actually helped in improving, that has actually helped in this popularizing this electric vehicle. So because power electronics, if you go back to that box, so here power electronics are used in a lot of places. Like for example, it is used in this onboard charger, it is used in this inverter, it is used in the DC to DC converter. So in all these places, power electronic like is used, right? So that technology has become very good. So therefore, these converters are now much smaller and much more compact compared to what they used to be in 1973, right? So apart from that, actually controllers like the micro processors and microcontrollers that are there, that technology has also improved because VLSI technology has improved. So that has helped in like the drive circuit and the overall energy management as well as operation of the EV. So those electronic circuits have also improved a lot. Right. So these are all the reasons why electric vehicle has become more and more popular. People are talking about electric vehicle a lot. So now let's see whether this is really well founded or not. Right. So if you look at the switches, okay. So because we said that there is a like definite evolution in power electronic switches over the years. So so let's see now what kind of switches are used where, right? So the switch is mainly like depending on the power rating, you select the switch. So in power electronic course, we were taught that there is an inverter, there is a rectifier. So for power electronic guys, they are all the same. They're like every switch will have a voltage rating and a current rating, and based on that, depending on the voltage rating and current rating, we select the switching frequency of the switches. Like for example, if you look at a RF amplifier used in a smaller consumer electronic device, so there the switching frequency has to be extremely high because the circuit is actually very portable. So whenever the circuit is very portable, like your cell phone, there the switching frequency of the converter has to be very, very high. Okay, so that is the way they make the converter size small. All right. So, but let's say you go to a solar farm of 1 megawatt. So there the switch need not be very, very small, because solar farm of 1 megawatt has a lot of space. So the switching technology is something else, so that the switching frequency is actually low, because you want to keep the efficiency very, very high. All right. So therefore, if you look at how the switch is used, so at very, very high frequency, you actually follow, you actually prefer GAN devices. In most of your cell phone, either GAN or high quality MOSFETs will be used. Okay, because that is the way they have made the cell phone lighter. So, but if you go for rooftop solar or solar PV or UPS kind of application, there you may use a MOSFET or an IGBT, silicon MOSFET or silicon IGBT. Sometimes silicon carbide is now being replaced, but the problem with silicon carbide is that with current system, it is actually having a difficult time competing with IGBT. IGBTs are much cheaper compared to silicon carbide. But if I tell you now, with many designs that we are doing now for the industry, we actually use silicon carbide because their prices have actually reduced. Okay, and India we are planning to manufacture silicon carbide MOSFETs in India itself, so that its prices can even be brought down further, right? But like if you go to, let's say, very high power circuit like HVDC stations and things like that, their line commutated switches are still very popular, like thyristor kind of a switches or IGBT with 1 kilohertz switching frequency. They are actually far more popular, right? So this is the story of switches and how you select a switch. Because the switch is actually selected based on the switching frequency requirement, right? If your power requirement is very high, the switching frequency has to be low, because you want to keep the efficiency very high. Switching loss has to be minimized, right? And if your power requirement is very low, then you keep the switching frequency very high, so that you can be portable. But their efficiency doesn't play a lot of role in selection of the switches, because like mobility is the main issue there, not the efficiency, right? Is there any questions so far, or can we go further? So let's go further. So now another technology that has improved in the last 10 years or so, this I have in front of my eyes, I have seen this changing, is this nanocrystalline core. So nanocrystalline core have see, the selection of core is actually based on the resistivity. Okay, so at very high switching frequency, we tend to use ferrite core. Okay, and at very low switching frequency, like 50 hertz kind of a thing, we use the CRGO core. The reason we use CRGO core is that because the resistivity, permeability of CRGO is very good, and the saturation flux is also very good, but it has a very low resistivity. Resistivity means it will lead to eddy current. So eddy current will be more in a CRGO core at 50 hertz. And as you know that eddy current is directly proportional to frequency square, right? So therefore, what happens is that like when you go for 100 kilohertz type of switching frequency, the CRGO core loss will be, it will heat up a lot. So therefore, people use ferrite core, which has a much higher resistivity. That means eddy current cannot flow very easily, because there are air bubbles inside a ferrite core. There are empty spaces where there is air, so the filling is not proper, right? So this ferrite core has permeability which is comparable to, sometimes comparable to CRGO core, but it has extremely good resistivity. Okay, so therefore they are used in very high switching frequency application. But there is a, recently there is something that has come up which is called nanocrystalline core. It is very, very common now in EV charger design. So the permeability is excellent. It is like maybe 10 times or 20 times that of CRGO, but it has decent resistivity. It's not like it is very bad or anything, but it has decent resistivity, right? So this kind of nanocrystalline core has become very, very popular in designing fast chargers. So if you are planning to design a fast charger, or if you want to design a fast charger, so more often than not you will be using a nanocrystalline. All right. So as we go up in frequency, so at very low frequency we will prefer a CRGO core, that is like this. That is why there are stampings to reduce the eddy current. And then as we go up in frequency, we will go towards a ferrite core, right? So ferrite core is generally used like at a frequency of hundreds of kilowatts, right? And then our megahertz range, you use a different type of ferrite. It's called nickel zinc. So that is actually very common in PCB based design, right? So in portable electronics based design, this ferrite nickel manganese is very, very common, right? So these are the two technologies that have actually improved in order to make the power converter accessible, right? So that is why I was telling you that the switches, we saw what are the type of switches that are used and at what power level, and then what are the magnetic core at what frequency level you use. All right. So then let's go forward. So if you look at electric vehicles, so the one that electric vehicle that we are actually concerned about is the battery electric vehicle. Excuse me. So battery electric vehicle is actually, it has only battery. That is the propulsion. You charge the battery, you move around, battery discharges, then you charge it again. But there are other electric vehicles as well. So something like a hybrid electric vehicle. So this is more common in India now. If you are buying a let's say S-Cross, there are other Suzuki has many, like Maruti has many other. हाँ, yeah.
सर पिछले 2-3 मिनट से आवाज नहीं आ रहा था इधर, जो आप स्लाइड पे थे ना इंडक्टेंस वाली पे, फेराइट कोर वाली पे, तब इधर कनेक्ट नहीं हो पा रहा था.
Oh, अच्छा. Should I go through it again? Is it okay?
If possible, just 2-minute break only. This slide only, yeah.
So actually here what I was pointing out was that this resistivity, okay, actually should I stop my video? Maybe that will save some.
That is okay if you stop video, yeah. That is.
So let me just stop my video so that stop video. Okay. All right. Hopefully it will be okay now. So am I audible now?
Yes sir, but sir स्क्रीन पे बीच में कुछ ब्लर जैसा कुछ आ रहा है, वो स्क्रीन को हाइड कर दे रहा है, स्लाइड्स को कुछ पोर्शन ऊपर और कॉर्नर में.
ये ठीक है. कॉर्नर में ये जो ब्लैक कलर का आता है ना, नाम कुछ है,
टॉप
वही प्रॉब्लम है.
हाँ ठीक है सर, अभी ठीक है.
हाँ, इसको मैं साइड कर दिया इसलिए पूरा
बीच में आ जा रहा है, बीच में और टॉप पे भी है, दो तरह की.
टॉप में भी चला जाएगा, देखते हैं अभी चला जाएगा शायद.
ये स्लाइड के कंटेंट को हाइड कर दे रहा है थोड़ा.
ये ठीक है अभी?
अभी ठीक है सर, अभी ठीक है. यस सर.
हाँ, तो ये आ जाता है, वो जो नाम वगैरह है ना, वो आ जाता है.
यस.
Okay, so this magnetic core, like see, at low frequency we prefer a CRGO core. We know that we used to design transformer using CRGO, and stamping, we used to use stamping. So the main advantage of CRGO core is that it has a good permeability and the saturation flux is very, very good, about 2 Tesla or so, right? But the problem is that it is like a wire, right? It is like, because when there is a change in the flux, it is actually introducing eddy current into the core. So this resistivity of the core is 48 microohms per centimeter. So that is a kind of low. It is like a good wire. Okay. So, but if we go for very high frequency, like 50, like 1 kilohertz or so, or 10 kilohertz, so then what happens is that this eddy current is directly proportional to frequency square. So this, like if you use a CRGO core there, the loss will be very, very high because it's frequency square, right? So loss will be very, very high. So therefore, at higher frequency, people use ferrite core. So ferrite core has a good resistivity. The resistivity means it doesn't allow eddy current to flow. All right. So but the problem with this ferrite core is that its saturation flux is kind of limited, which is okay for us because most of the time ferrite cores are not used at the power level of the CRGO core. It is only for power electronics application. But with advent of EV chargers and EV charging systems, we actually need something in between like CRGO and ferrite, and that is given by this nanocrystalline core. So nanocrystalline core has a decent resistivity, but it has excellent permeability and saturation flux. So most of the fast chargers that we are designing right now will be a nanocrystalline core based design. All right. So is that okay?
Yes, sir, yes.
All right.
So I have one question here. Like,
please.
if we are using a ferrite core, so does the size, if we don't have any, let's say from academic research point of view, if we don't have any constraint on the size of the converter, so whether to use ring type ferrite core or E type ferrite core, does it make any effect on the performance of the converter? If inductance we get whatever you want.
Actually, see, most of the time, toroid core, there is a like limitation to toroid core, what it can do. The reason is that E core, you can actually introduce an air gap. Okay, so by introducing an air gap, even though the inductance will go down, but the saturation current will actually go up. All right, so that is not possible with a toroid core. But many a times when we are designing the input filter and things like that, we actually don't need a lot of inductance there. Okay, so there it will be beneficial to use a toroid core. So what I am trying to answer your question, what I feel it's a design thing. Like if you are getting away with a toroid core, then absolutely no problem. Okay, because size wise you have to follow the procedure that is given in, let's say, Ericsson book and all, and that will give you the which size of core you will be using, right? But it doesn't actually make a difference as far as toroid or E-core is concerned. But E-core gives you an advantage that if tomorrow you have a problem with saturation, in E-core you can actually slide a little bit of thing and increase the air gap very easily. Right, because you are actually putting two E-cores in, so you can actually put some paper or something on two sides. Let's say if you can see my let me see if I can put a pointer here. So here, if I put a paper and here I put a paper, then I'll get an air gap here, right? So that is very easy to achieve in E-core.
Okay, thank you.
So if I go to electric vehicle, battery electric, so battery electric vehicle is like, it is completely like you have a battery there. There is no petrol or gasoline there. So you charge the vehicle, you move around, battery discharges, and then you charge it again. Similarly, with this is more common. Hybrid electric vehicle is more common right now. So what happens here is that we actually have we put actually petrol, gas means gasoline is petrol, and then we move around. And when we are braking, there is a battery that will be charged that will be actually powering the electronics of the electric of the vehicle. So that way some saving in energy you will have, some saving in petrol you will have. I have seen that in my vehicle as well. I have a S-Cross which is called smart hybrid electric vehicle, smart like vehicle. So like a smart hybrid they call it. So that is like a hybrid electric vehicle. So but the point that we are trying to make is that in hybrid electric vehicle still petrol will be used, but in battery electric vehicle there will be no petrol. And then there is a plug-in electric vehicle which is kind of in between. But we actually are In India, we actually mostly see hybrid electric vehicle or battery electric vehicle. Okay. So now the question that I always had was that like when you have these electric vehicles and we have a battery, we have to charge that battery. So that charging takes some time. Okay. Now the most of the time the concern that people have, or the wish list that the people have, is that can we charge it in a very fraction of time. Okay, so that is one of the concern, right? If you can charge the battery in 1 minute or 2 minutes, then it will be very close, very similar to a gasoline electric vehicle, and electric vehicle will sell. So this is one of the questions that I had in my mind, and then when I thought about it, actually this is the answer that I got. See, when we see a building, okay, let me do this, right? So when we see a building, we can see that a building can be built in 3 months. So a building can be made to go from, let's say, 30 meter to 100 meter in 3 months. But if I look at my daughter, or if we look at our kids, right, then we see that like it takes them 13 years to go from being few centimeter to let's say 1.5 meter, right? So while a kid takes 13 years to grow from 30 centimeter to 1.5 meter, and a building only takes 3 months to grow from 30 meter to 100 meter. The reason is that, listen to this, the reason is very interesting. See, when you are talking about a building, we are talking about a lot of workers working in that building. The workers are eating, they build up energy, and within a day they are putting that energy into the building, the structure, right? So therefore, like all their like energy that they are acquiring, they are actually putting it into the structure in a very small span of time. That is why the building is growing very fast. Okay, but if you look at my daughter or our kids, they actually, it is a chemical process that happens. They eat, they like live their life, they do all their daily activity, and slowly they, so it's a chemical process. So that is the difference. This picture is the difference between petrol and battery. So in petrol, Mother Earth has taken thousands of years to build that petrol, right? And we are actually putting it into the car and basically burning it within a small span of time. But when you are talking about charging a battery, it is like our daughter growing up, because battery is like a chemical system, right? So in order to charge a battery, you take certain amount of time, right? So now, does that mean that we can do the charging very fast? Yes, we can do the charging very fast, but that will come at a cost. So what people say is that even though if you use fast charging every day, then your battery will degrade. Okay, it is something like if you take some kind of drugs every day, then you will be in trouble, right? So something like that. So you cannot force a chemical process beyond a certain point. So that is the whole idea of it. So, and that is why that is actually the main drawback of an electric vehicle, that it actually uses a battery which is a chemical system. Okay, and it takes certain time to replenish the charge and things like that. Hopefully I made this thing clear. So if I go forward, so if you look at the electric vehicle, there are two different systems that are there in the electric vehicle. One is a 12-volt battery system, another will be a high voltage system, 320 or 350 volt battery system. So this 350 volt battery system is powering they call it the powertrain. Powertrain means it will be the battery, the inverter, the motor, and motor is simply like connected to the transmission of the thing, right? And then when the battery gets discharged, we have an onboard charger to charge the battery. So this will be this drive train. 320 volt bus system. But there is also a system which is like the 12 volt system, all them electric mirror, power steering, seat adjustment, music system, all these things are run by the 12 volt system. So if you go inside a normal car and an electric vehicle, then you will actually not find any difference because they have made sure that this 12 volt system is intact. Okay, the seat adjustment, the music you hear, they are all intact. Okay, they are all same as what a normal car has and the electric car has, but only the transmission system has been changed, right? So if you look at how to charge the electric vehicle, like I already pointed it out, that so we have two types of charger. One is a AC charger, which will use a onboard charger. That means the charger will be on board. Okay, so AC will be converted to DC, and then DC will be charging the battery. Or there is an off-board charger where this small charger, as it is inside the vehicle, it has to be small. But if you can remove it to the outside, then it can be very big. Okay, so that big thing is called a fast charger. So that will directly give the DC power to the battery. But now think about like when to use a single phase and when to use a three phase. So a plug point in our home is 16 ampere is the highest plug point that you have in your home. So 16 ampere times 230 volt will come out to be 3.5 kilowatt also. So 3.5 kilowatt up to 3.5 kilowatt we can do inside our home. And if you actually ask for some novel system from your electric company, they can actually provide you a 32 ampere plug as well. So 32 times 230 will be the maximum power you can draw from a single phase. Right. Now, if it is above that, let's say you want to draw 50 kilowatt, 60 kilowatt, then it has to be a three phase. Okay, so that is where the difference in the supply comes into picture. So when you are using a onboard charger, it will use a single phase, and when you are using a off-board charger, it has to be a three phase because the wattage rating is much higher than what the home supplies can supply, right? So if let's think about what is inside this charger. So if you look at what is inside this charger, these are all converters basically. So we know from power electronics that there are four types of converter. One is a DC to DC converter, DC to AC converter, AC to DC converter, and AC to AC converter. This converter is not that important because actually modern day this converter has been replaced by a rectifier in cascaded to an inverter. Okay, if you cascade a rectifier and an inverter, then you get a AC to AC converter, and that is precisely what is happening in your washing machine, right? In your washing machine, you have variable frequency drive, right? So the washing machine is moving this way, that way, so variable frequency drive. So that is actually using a rectifier and an inverter in cascade. Okay, but previously when initially these things were done, people used to use something called cycloconverter. Okay, so in cycloconverter you can only go down in the frequency. So that was used much before, like when traction, like electric traction, in 1900 it was used, right? So that was, but nowadays it is mostly a rectifier cascaded with an inverter. That's what you will have. Now, if you look at a converter, the converter has two parts. One is the power stage and one is the control stage. So the power stage, power stage is actually taking care of the power, and control stage is making sure that the converter is regulated, right? So if you want to regulate the output voltage, then you actually use a controller and feedback the circuit, and so that is the job of a control stage. So when you look at a converter, it will look a single structure, but inside it there is a power stage and a control stage. Okay, so now how does that matter? See, the reason it matters, why I was showing you this picture, was that at the end of the day, when you are having a battery, you have to do CCCV charging. You have to charge the battery with constant current and constant voltage. So what is this? So what is this is that if you have a lithium ion battery, then when the battery is discharged, like it has a low SOC. When it is discharged, it is called a low SOC. So then you charge the battery with constant current. Okay. So and like the SOC of the battery will increase, and once it has increased to certain point, then you charge the battery with a constant voltage. All right. So that is called CCCV charging. So in other words, the converter that you are having has to work like a current source when the SOC of the battery is low, and has to work like a voltage source when the SOC goes high. So that is shown in this picture. When the battery SOC is low, battery SOC is known by the way you know the SOC is low is if you look at the terminal voltage of the battery. If the terminal voltage is low, like in a 12 volt battery, the voltage is 12 volt, then you know that the battery SOC is low, because a fully charged 12 volt battery will have a voltage of about 14.3 or 14.4 volt. So at 12 volt, you actually charge the battery with a constant current. So the charging will be very, very fast if you charge it with a constant current. And once it has kind of charged to, let's say, 80% of SOC, then you move to CV charging, that is constant voltage charging, so that then like now very, very easily and very, a lot of time you can charge. Fully discharged battery, the voltage will be around 11.5 or something like that. We have seen up to 2.2 to 11.5, around that value we have seen. So now the point is that this is called CCCV charging. And the reason we have to know CCCV charging is because when you are making this charger, we are actually trying to make this charger. So that has to work like a current source. And the same charger has to work like a voltage source. Okay, when SOC is low, it is working like a current source. And the same charger is working like a voltage source after the SOC has gone high. So how does that happen? How do we make the same converter work like a current source and a voltage source? That is what we will see next. Any question? Okay. All right. So please type it in if you are unable to speak, or I am not giving you enough time to speak. Then just please type it in. I can answer it. Right. All right. So now if you look at any converter, let's say I take a buck converter, any converter, it doesn't matter. And if I feedback the output voltage and regulate it to a value of reference, then actually in principle, what I have done is I have made this converter a voltage source, because no matter what the load is, this voltage will be fixed to this reference or a gain of this reference. Okay. So this feedback circuit, by taking the output voltage as your feedback, you have regulated your output to reference voltage. That means you have made your converter a voltage source. So if you put a sine wave in the reference, the output will also be a sine wave. But no matter whether the load changes or doesn't change, or the input changes or doesn't change, the output will be fixed. Okay, because the feedback is making sure that it will be fixed. Is there any question?
लास्ट 1-2 मिनट से हैंग हो गया था सर, 1 मिनट, लास्ट 1 मिनट.
That's one. All right, so let me go back. Tell me where was this SOC thing okay or no?
Yeah, this was, I think you have explained here. Sir, I had one question here. That why 80% only, why we do not charge in CC mode up to 95%, let's say near to V reference and for.
So this was Manmohan, it's actually a great question, because I also had the same question, and when I talk to my friends in see, the beauty of working in CART is that here there are chemical engineers, there are mechanical engineers in one center, right? So when I talk to them, they said that this when you SOC actually goes up, there is a change in the like internal resistance of the battery. Okay, and if you actually charge it with constant current, then more loss will be there than the charging, and that's why the fire will be there. If it will like lead to fire. Okay, so that is.
So this 80% is kind of thumb rule based upon experimental analysis kind of thing.
80, 85, 80, 85, 80 is a ballpark number, sometimes it's 75, 80, 85. But around that value, you have to convert, you have to go to the voltage. You cannot basically force a current now after that.
This is valid for lead acid as well as lithium ion. This 80% around.
No. Lead acid has a different. Lead acid anyway you cannot charge at a very high current. My experience is that at 0.6 of a 0.6 or 0.7 SOC, lead acid battery will have problem. I had a 12-volt battery. I started charging it at like 19 amp or so. I had it was heating up actually. There was smell. Okay, so it was heating up. So what? I mean, this is just, I was just trying to see where is the limit is, because when you read papers, they will give different numbers. So you have to be very careful about reading papers and materials nowadays, because most of the time they are advertising in these papers. They are less to do with reality and more to do with advertising and selling their product, right? So that is why as researchers we have to do that. So yeah,
let's say it is like 60%, 70% we can do CC and we can go for CV.
Yes, we can go for, but even at CC also the current has to be low in case of a. And in case of a lithium ion battery, the current can be very high. Like for example, if you are let's say a 5 ampere hour battery is there, you can actually charge it with 10 ampere. Okay, 2 times. You see they call it. Okay, but to that like 10 ampere, you have to desert that 10 ampere charging as soon as the SOC has reached 80%.
80%, yes, obviously.
85%, right? So that's the point.
Thank you, sir. Thank you, sir.
Okay, so let's go forward. So now the question is that the same converter is actually becoming a current source, and same converter is also becoming a voltage source depending on the SOC. At low SOC, it becomes a current source. At high SOC, it becomes a voltage source. How does that happen? Okay, so this is actually happening because of the feedback, voltage feedback and current feedback. So if you are taking output voltage as your feedback, the controller is making sure that the output voltage is fixed. Okay, therefore the converter has become a voltage source now. No matter whether the load changes or input changes, the output voltage is fixed to Vref or a gain of that Vref, right? So therefore it has become a voltage source. Now, if instead of the voltage, if you feed the current to the feedback circuit, then it will force a current output. So that is how you actually convert the same converter to a current source as well as a voltage source. So basically what they will have is, they will have a current loop and parallelly they will also have a voltage. Okay, so if the SOC is low, then the current will be given to the feedback and the converter will be operated like a current controller, and when the SOC becomes high, the current converter will switch to a voltage controller. Is that concept clear? Current source and voltage source. Is it okay? Am I audible? Hello?
Yes, sir, we can screen.
Okay.
Yes, sir.
Okay. Yeah. Sometimes I get stuck, so you have to. Yeah, I am asking this question because I'm not able to know when I'm getting stuck. Right. And so now let's see how this charging happens now. So like we have a fast charger, we have an electric vehicle. So electric vehicle is a DC source, fast charger is supplying a DC output. All right. So this DC output has to become a current source and as well as a voltage source depending on the SOC of the battery. So in order to know the SOC of the battery, there has to be some kind of a communication. The battery has to tell the charger that this is my SOC. Based on that, it will make it a current source or a voltage source, right? So when the vehicle actually tells the electric like the charger that it has low SOC, then the charger will become a current source. Okay, and what that current source means is that like it will become something like this. It will become something like this. It will actually feed a current and try to force a current to the output, right? And when the SOC becomes high, the same charger will become a voltage source. In other words, instead of a current controller, it will work like a voltage controller after that, right? So that is why how the, but in order to do that, there has to be constant communication between the electric vehicle and the charger. Okay, that has to be there. So how does that happen? So this communication has to be always there between the electric vehicle and the charger. So this communication, in order to have this communication, if you look at the plugs of an electric vehicle, there are three main communication pins. So there is a CP, PE and PP. Okay, so there are three communication pins. So most of them are very easy to understand. One is proximity pilot. So proximity pilot, what it does is that so proximity pilot is basically taking care that whether the cable, whether the plug that we are having, this plug is properly connected to the electric vehicle or not. This plug is here and this is here, right? So this plug has to be inserted into the electric vehicle, right? Electric vehicle like socket, right? So that connection is proper or not is actually taken care by this proximity pilot. And how does that do it? Actually, if the connection is not proper, then the R cable will be very high because the connection is not proper. So if a voltage is there inside the car, then a very low current will flow to the known circuit of the charger, right? Because the R cable is very high, right? But if the connection is proper, then the R cable is almost equal to 0. So the current will actually increase. That if you have a known voltage, let's say 5 volt or something, and a known resistance of 1K, so normally you should have 5 volt divided by 1K if the cable connection is proper, right? So if it is not 5 milliampere, if it is much smaller than 5 milliampere, then you know that the R cable has not been connected properly. So that is how proximity pilot actually works, right? Then the second one is the protective earth. Protective earth is because the vehicle doesn't have a ground. Okay, the car doesn't have any ground because there is a tire, right? So the tire is insulated, right? So all the grounding will happen actually through the charger. So therefore the charger should have a protective earth. So every charger, let's say if you look at any charger, let's say this charger, whenever the charger will be installed, like in a building, there will be a proper earth that will be dug in and put there, because that earth is paramount for this electric vehicle. Any problem to that earth will actually blow electronic components inside the electric vehicle as well as inside the charger. Right, charger is not none of our major problem because charger is not our thing, but electric vehicle is bought by us, right? So if any due to any issue in the ground, if my vehicle doesn't the electronic circuit damages, then it's a very big problem for me because now I have to spend a lot of money to fix that thing, right? So that's why this protective earth is one of the most important thing in our Indian context, because Indian system, power system, the earth is not actually proper. All right. So in case of electric vehicle, this earth has to be absolutely proper. Otherwise, we will have a lot of trouble. So we talked about proximity pilot. We talked about protective earth. Now let's talk about the CP, right? Control pilot. So this control pilot is the one that is actually communicating with the electric vehicle regarding what is the SOC of the battery and whether it's a DC charger, AC charger, what is the thermal status of the battery. All these things are actually communicated to the charger through this control pilot. It is actually some kind of protocol will be there, which will be kind of used to like different companies, different let's say CS2 or CHAdeMO, they use different type of communication protocol for this, right? So, but this is the pin that is actually providing the charger and the electric vehicle information about the status of the battery, right? So this is how the electric vehicle charger will look like. We have a fast charger. So we have some kind of a convert. I will not go into power electronics here because that's not my purpose. But I just want to give you an overview of what is happening. So there is a AC supply, then there is a PWM rectifier, then there has to be an isolation circuit. So the reason I'm showing you this circuit is that because this circuit will be very important for us when we are designing charging infrastructure. Okay, because when you are designing charging infrastructure in this two-stage design, this front end stage is taking care of all the grid code compliance, right? TSD has to be below this, or input current has to be this much, or all this grid code protocol are taken care by this front end stage. Okay, and all the communication between electric vehicle and the charger is happening in the second stage. Okay, so when we are saying that there is the CP pin is communicating with the charger, actually the CP pin is communicating with the controller of the second stage, DC to DC converter. All right, so that is how the division of work is as far as the charger is concerned. The front end stage is taking care of the grid, power factor, TSD, any other thing, and the second stage is taking care of the electric vehicle charging, right? So if you look at the charging, what is the impact of a charger on the grid? We are talking about fast chargers as well as slow chargers. Let's say we in India 30 lakh vehicle is sold every year, right? So from that, let's say 30% becomes electric vehicle. So it's a big number, but let's say 30% people buy electric vehicle. So, and most of them will charge it at night. At 80% of them will charge it at night. So what that means is that straight away increase of 792 megawatt. So around 1 gigawatt of extra power will be needed, right? And that is a very easy assumption here. And let's say there are a lot of people will use a fast charger, let's say 50 kilowatt charger, and let's say 100 vehicles start using 50 kilowatt charger at the same time, which is very easy in a place like Delhi, right? In a Delhi where many vehicles are there, and 100 people, 100 is nothing, right? 100 car will be there inside IIT, there will be 5,000 cars, right? So from that 100 car, let's say start charging at 50 kilowatt fast charger, then 50 kilowatt times 100 vehicles is 5,000 kilowatt, right? So like 5 megawatt of instantaneous energy requirement, right? Very instantaneous energy requirement in a very short span of time, in a very therefore there is a problem in like making this installing this fast charger. So in order to do that, so there is a grid, there is an electric vehicle, and let's say the charger is 50 kilowatt. So that like hundreds of them will actually create a lot of problem for the grid. So in order to solve that, every like going forward, even though it is not happening right now, going forward, all EV charging infrastructure should have storage. Okay, they have to have storage, and that is where all these vehicle manufacturers are thinking that they're like whatever battery they are using, the second life they will use for their storage. When the battery is basically removed from the vehicle and new battery is being put, the old battery can be used as storage, right? So the storage is like a cushion for the electric charging infrastructure, right? Like if you look at a charging infrastructure again, like there are many types of control that will be there. So if you think about it, if you just imagine this, like you have an electric vehicle, you want to go to a charger and charge the vehicle. So what will you do? You go and then park the vehicle first, and then you remove your some kind of a RFID or your credit card or something, and then insert it, and then it recognizes that you are this person, and it will say that okay, you now take the charger and plug it in. So you take the charger and plug it in. So in all this you can see that there is a, like whenever you are inserting your credit card, there has to be a communication between the charger and the whole world through the internet, right? So that money can be exchanged, right? So now there is another aspect to it, that before even going to the charger, you will look at your cell phone and see whether the charger is free or not. So how does that happen? So then there has to be a communication between the charger when it is occupied or not occupied and the internet, so that you can know whether the charger is free or not. So in these are the things that I am telling you, because what that means is that every charging infrastructure will have layered control. Okay, one control very easy, converter को control कर दिया. So like I was telling you that you make it a current source or a voltage source. Like I was just telling you here that you make a current source. So this is called a primary controller. That means it is directly controlling the charger. So now if there is a battery, okay. So this battery will be called the secondary control. So the control of power through that battery, like here, like control of power through this battery will happen through a second. So it is not actually controlling this, or it is actually some brain is telling you when to use the storage and when to use the grid, right, for charging. So that is like the secondary control. Okay, so that is like the secondary. And the tertiary control is like all the communication with the grid, with the internet, and financial transaction. All this will be tertiary control. So obviously the primary control has to be very fast. Secondary control will be a little bit lower speed, and then tertiary control will be very low speed, because tertiary control will happen in seconds. So these are the layered control that you will have in a EV charging infrastructure going forward. Even though some of them are there right now, there are many things that are missing, and there are like all these Western companies are basically jumping up and down to give their technology to India, but I think India should develop it. Itself. All these startups are actually recognizing that this is a problem and starting to work on it. Right. So now EV versus our society, right? So in order to make EV viable, the society also have to accept it, right? So what is that is accepting about it? So charging, distribution of charger in a certain area, cost versus time, local customer support, resale value, all these are customer awareness that are happening for the society to accept whether EV should be there or not. Okay, and in order to make EV viable, what policymakers are right now doing is education, like this program, this particular faculty development program. These are all initiatives by the government to make people aware that this is there, and this is where you can actually contribute to the technological stuff and make money and things like that. So some of the things that is killing of manpower that I'm talking about. But there are other problems that policymakers have, is that once the battery is done, it is kind of used. What do you do with the battery? So they are actually thinking of that. And instead of lithium, can we use something else? So many researchers around India are actually spending a lot of time on having, let's say, sodium-ion battery and magnesium-ion battery, etc. Right? So what policymakers are saying is that okay, if these batteries are not as good as, let's say, lithium ion, that is also fine. If it is, let's say, 80% as good as lithium, also it is fine, because it will be under our control. We don't have to source lithium from external countries, right? So that is why this awareness of the society and how people think and how the policymakers think also make a lot of difference about EV. So currently the way it is, we have completely accepted EV in two-wheeler and three-wheeler sector. Actually, if you think about it, in a two-wheeler and three-wheeler sector, we have actually accepted EV. But let's say when we go for, let's say, four-wheeler, that is where the problem is. In the cities, still it is enjoying a better luck compared to in second tier cities as well as rural areas, because there the problem of charging always comes into picture, right? So with this, I will conclude my presentation. But I wanted to just show you that we, with like IIT Delhi, we work a lot with many companies and like develop product for them. So this is one of the products that we developed for American battery system for one of their grid tied battery. Okay, so there they wanted to use a converter for using the power, like battery power. The BESS, the battery energy storage system, has a battery voltage of 1500 volt. So that is not useful for people. That has to be converted to a lower voltage for it to be useful. So that they wanted. So we actually developed a commercial. This technology was actually transferred. It's a commercial thing. And then we have residual sensors, current sensors, etc. Also, we also did that. And there are some solar inverters, etc. Also, we kind of did for one of the companies, right? So I am kind of stopping it here. We can discuss one more. We can discuss if there are any questions or any concerns that are there, right? We can spend 15-20 minutes on that.
Sure.
Yeah, please. I don't know whether you can type it in or you can talk also. Some of the participants want to question. I don't know whether. If you can type your question, I can answer, or you can just talk through. Manmohan, how is it? I mean,
Yes, sir. Yes, sir. So whoever want to ask question, please raise your request so they will unmute you particularly. Start continue, please. With the time for questions.
So I'm actually done. I mean, I just wanted to show you some of the products that we have developed, but like if there are questions, I can answer them.
Yes, so if any question, please let us know.
Yeah, good evening, sir.
Yes,
Am I audible, sir?
Yes, please.
So, in fact, this is practically applicable for the upcoming projects also. The theme you have presented here is very good, sir. We are greatly indebted to have this session. Apart from this, can we have any reference book for further study, sir, suggested by yourself?
See, normally this is a very new field, and many of the problem with book nowadays is no one is putting time into writing books.
Exactly. All our presentations.
All our presentations and also some papers they are putting, and then some books. I mean, it is not bad or anything, but thing is that when you write a comprehensive book, you present many aspects of it. But from my side, Narendra, what I can do is that I can share these slides with you.
Sure.
And if you have any questions, please email it to me, and I will try to answer it. Because the purpose here, Narendra, and for others also, is that people are becoming too defensive about protecting their knowledge and this and that, right?
Yeah.
Like through patent. But I will tell you what the problem with that is, because I come from the industry. So let's say Narendra, I have a patent, let's say, and let's say your company, let's say steals that. I'm not saying, just don't mind my words, but let's say they use that patent and don't give me any recognition. I mean, do I have the time to go to the court? I mean, with my present engagement, who has time to go to the court and fight and then prove that someone has taken? Actually, this patent don't mean anything. Like protecting this thing, actually, I don't know how. Let's say GE decides to steal your patent. What will you do with to GE?
So
Nothing.
my practical approach towards EV charging vehicles, I have done a few projects as a consultant, sir. There, the client is more dependent on the EV charging vendor companies about the technology, what is they need actually to do the business, the charging and all. All these concepts are not available in the market. Nobody is bothering about the evolution of the technology. So they
Oh, I lost you. Narendra, I lost you. One more, I lost Narendra.
Yes, he's not audible. Narendra ji, can you please reconnect or again ask your question, please? Maybe he'll join in certain time. Then any other person, please? Any questions?
Hello, sir. So my question is, what are the disadvantage of lithium-ion battery, other than that it is not easily available?
See, that is the best you have. I mean, can there be a battery that can charge faster? We don't know. Research is going on, but at the present time, it actually provides a lot of advantage compared to disadvantage. But the major, like what you pointed out, is correct, that the major disadvantage that we see with this lithium-ion battery is that sourcing of lithium ion and second life of lithium ion. What will you do with lithium ion once it is done? Okay, so people actually say that, oh, we will. We had a few companies. I mean, you will be amazed how these Westerners do business. Actually, there was a company. There are a few. Actually, it's not company. It was state-sponsored people. State-sponsored means through the embassy they came. Okay, European people came to IIT Delhi. Being in IIT Delhi, that gives a lot of advantage. And their concern, or they were trying to tell us that they already have technology where you put a lithium ion and all the materials will come out. Okay, all the useful material will come out, and they want to sell that product to us. They were not concerned about the lithium ion. They said that lithium ion, we know that there is a problem. We have a machine where you put these old lithium ion batteries, and on the other side, all the useful material will come. And knowing India, I mean, you being an Indian and me being an Indian, I mean, we are always looking for turnkey solution rather than developing anything ourselves, right? And people are so happy that, oh, wow, wonderful product. I mean, you should be making it yourself. I was thinking in my mind that, come on, you should be, I mean, we should be thinking about it and making it ourselves. But your question is that what are the disadvantages of lithium ion? At this point, that is the best we have. But the only, like you already pointed out, that getting sourcing them and what to do after that is what the concern is.
Sir, my another question is, in all the three types of control system which you had showed, primary, secondary, and tertiary, other than PWM, we can use other control techniques also, like adaptive or sliding mode or something different?
Yes, that's absolutely fine. Absolutely fine. See, at the end of the day, you have to make it a current source, right? So how you make it a current source is dependent on. See, normally sliding mode that you call, I call it hysteresis current controller. So this hysteresis or sliding mode current controller has very good dynamic response. Okay, that means if there is a change in load, this converter will be able to follow that load very, very fast. But that is not required in a battery charging, right? Battery charging happens in, you think about your own cell phone ना, वो तो आप लगा देते हो, बैठ जाते हो, तो it happens in minutes. A very, very slow charging system will also work. Okay, so when with Manmohan, when he was in Kanpur, I remember we used to discuss this. Manmohan, if you remember, I used to discuss this with you. That in like Behera, like Professor Behera works on a lot of like a drone kind of a thing at that time, or even like mechanical control, right? So there the timing is not an issue. The timing is in seconds, right? So a PI controller will always work there because it's a slow controller. It is very stable and very, very reliable. It will always work. Like so therefore it is like lot of equations etc. are not required at that time, or lot of complication in control is not required. But let's say you are powering, let's say a server. Okay, so server, the control has to be very fast. Like I used to work for this company called Infineon, where we used to make servers, right? So there I have to use very, very fast controller, very, very. So sliding mode is one of the controllers I used to use. And I didn't call it sliding mode. I used to call it a hysteretic controller. But yeah, that is what I was actually using at that time, because that is what was giving me the fastest response, right? So to answer your question, actually, yes, you can use the controller, but remember that when you are venturing into EV, you are actually venturing into commercial space, right? In commercial space, reliability is far, far more important than what greatness you have in your controller, because no one knows what is inside your controller, but everyone will know whether it works or not. I'll tell you a story here. When I was at IIT Kanpur, I was leading a project, is Indo-US project, big project. Okay, so as a part of that project, they said that they can put solar panel on top of my house. Okay, so I flatly refused that. I said no solar panel on top of my house because I'll have other kinds of problem there. But let's say there was a senior professor who actually had solar panel on top of his house. So and he was very happy that he had solar panel on top of his house. So I told him on that day that sir, आप लगा तो दिया आपने, अब मैम से गाली सुनना पड़ेगा आपको ना, क्यों? मैंने देखिए सर, मैं अभी क्यों बताऊंगा आपको. And after 5 days he said that I got a severe scolding from my wife that why did you put this solar panel. And the reason why ma'am was very upset was when there was a power cut. There was a power cut in IIT Kanpur. The solar panel didn't power the house. The power cut, the solar panel also went. Then she was asking that you have a solar panel, it is supposed to feed you power when you have a power cut. Why it is not happening? Then he asked me why it is not happening. I said, sir, the battery is not there. That is why it is not happening. So you have to put battery there. So what I'm trying to tell you is that, so when you are going into commercial space, people don't understand what is the technology used or how great a technology used, but they will understand what is happening, right? Like we don't know what is inside a cell phone, but we can clearly see whether the cell phone is lighter or not, whether it is, we are able to talk more or not. So when you are venturing into commercial space, always try to see what people want and then try to feed into that, right? Because you are from academia, that is why I'm suggesting you this. Did I answer your question?
Yes, sir. Yes, sir. Thank you so much, sir.
All right. Is there any other
Any
question?
other questions?
Hello, sir.
Fine.
Sir, I'm working on like LLC converter, just you have shown in the battery charger configuration, right?
Yes.
So my question is that generally the other converters operate in the like PWM techniques, but LLC is like frequency, resonant frequency converter.
Right.
So only problem I like faced is like operating it in the light load condition, like in the starting. So there is a huge ringing and many like in the transformer waveform also the ringing is very prominent. So what is the starting suitable technique to start like LLC converter at very light load condition?
See, like, are you having a battery at the output or resistive load?
Resistive load, sir. Generally, like it is an onboard charger, but for being while we are using the electronic load, like we can say, I can say.
So that is where the problem is. See, think about it this way. Just now you said that it has to work in resonance. Look at my, can you see the dot?
Yes, yes.
Pointer. See, this is a L, C, and there is a R here. You don't have the battery, right? So there is a R. So then there is a resonance there. So at light load, this resistance is very, very big. Okay. And when the load becomes higher and higher, this resistance will go down, right? So,
Yes.
see, LLC converter is not designed for resistive load. Okay, the reason why they use LLC converter in onboard charger is because there is a battery. Because there is a battery, the voltage is actually kind of fixed there. Okay, the voltage doesn't change a lot. Okay, so the voltage is fixed, only the current is what you are basically. What I will suggest is that you replace your resistive electronic load with a battery. Okay, even though like it is a small battery, small converter, that's also fine. But try to replace it with a battery and do the same thing. I think you will have a better response, and that is precisely why LLC converter is used. In fact, LLC converter is not a PWM converter because you work on it. It is actually a frequency control, like pulse frequency control you are doing, because like you are actually tracking, like with the load, you are actually tracking the resonant frequency. Okay, so that is one of the beauty of like a LLC type of converter. So I will suggest that you first thing is that you make the converter similar to the intended application. Intended application is onboard charger, which is having a battery at the output. Right. So let's first make that, and then you do the experiment. And still, if you have a problem, just email me. What problem you are facing?
Sir, just adding to your point. Suppose if I am added the like in place of electronic load, I have modeled it like a battery. Okay, so if I am not going directly, like if in that case I have to control the current also. Am I right?
In either case, you have to control the current. See, at the end of the day, you have to do CCCV charging, like I told you. No matter what the converter is, okay. In constant current mode, you have to make your converter work like a current source. When the SOC becomes high, you have to convert it to voltage. So this is not negotiable. You have to make it a current source and you have to make it a voltage source, because otherwise like you will not be following the requirement of battery charging, right? So in other words, what we are saying is that if you go to your converter, you have to force it in a current control mode. You have to force that this current is constant. This current is actually constant in low SOC of the battery, and this voltage is constant during high SOC of the battery.
But what if I am going with the open loop condition?
What is open loop condition?
Like not giving the just PWM pulses, but not feedback to the feedback of like battery voltage and current.
No, then it's not a current source. So see, if you are trying to learn about the LLC converter, that is fine. But this LLC converter is very good when it is working as an onboard charger, right? That is why in onboard charger, if you look at Infineon will give you the complete design details, like starting from zero to how to make an onboard charger, like whatever onboard. I am pretty sure they are not able to sell their onboard charger. Otherwise, why we are they giving their details, right? So, like that detail is actually available on the internet. But the point I am trying to make is that first, put your converter to the intended application. That means have a battery. And once you have the battery, then you have to make it at CC and CV. If you are just doing, let's say, open loop, then you are trying to learn about the converter. You are not trying to do CC CV charge, right?
Yes, yes. Like we have the like what I can say is like we have the board, okay, and we are in the testing phase. But what we are facing is like operating in the in the light load condition. What I mentioned earlier also.
See,
So
at light load condition, the LLC is not performing properly because is a resonance, right? So it is
yeah,
probably in the inductive region or something because it has to be in
yes,
the
yes.
capacitive region, right?
Mm.
So it's probably in the inductive region. That's why it's not connecting properly, right? So
Okay,
you can change the like LC so that the resonance kind of point moves and maybe it will be okay, right? So.
okay, okay.
That is open loop. You are trying to understand the converter in open loop. You don't have to test it. You just can simulate in LT-Spice and you will see this behavior actually.
Okay. Okay.
Yeah, any other question?
Any other question, Cherry, please? Sir, I have one question. Like we have this mobile chargers, so let's say 80 watt or 67 watt something, and there is on output side they have written 2-3 ratings. Now when we put this charger to any mobile, maybe the any model, then those mobiles are having different batteries, different size, all those. So in that case, this charger, how does it decide that uh, at which current level I need to charge this? Whether they also communicate with batteries or how do they decide? Because they charge every battery.
So if I just took the Lenovo charger of my ThinkPad. So it says three outputs they are saying. It is saying 20 volt 3.25 ampere, 15 volt 3 ampere, 9 volt 2 ampere, 5 volt 2 ampere. Okay, so this is what this is saying. So what I think Manmohan it does is that whenever you connect it to anything, because then it is actually terminal voltage of the battery it is first sensing, okay, and feeding back. Based on that the current is decided. The first thing it does is that it is basically because as soon as you connect it, the charging doesn't start. If you see,
Yes.
you plug it to your cell phone, you will see that it will take 2 seconds or 3 seconds to start charging. Because
Yes.
what it is probably doing is that the voltage, whatever voltage, terminal voltage of wherever you have connected, that terminal voltage, it is actually feeding to the control system or the brain of that charger, and the brain of the charger is deciding what should I limit the current. Okay. So that is
Okay.
how probably it is.
So, sir, like everything is within the charger itself, right?
Should be within the charger, no? Because externally we are not doing anything, right?
But
We are only
even
plugging it in.
I think in some cases it like depends upon the battery or some circuitry inside mobile also. Like many chargers do not support fast charging for others. Like it's say I'm using OnePlus mobile with me, and if I'm putting its on charger, then that will support the fast charging. And if I'm giving same charger, putting same charger to another mobile that supports the fast charging, but with this charger that will not work. That will
Oh, acha. So there is what you are saying is that there is also a communication between the mobile and the plug, right?
yeah,
And the charger.
maybe yeah.
There may be. Yeah, there can be. Yes, because mobile also needs to protect itself. Na? If the charger goes mad, then mobile has to protect itself, right? So that is probably they will limit the current and things like that. Yes.
Even sir,
Yes, that
like
is
you
what-
mentioned, these 3-4 ratings are there, but let's say fast charger is there, and if we use it even in keypad mobiles, let's say with that normal cable, earlier cables, then also it will charge to that also at that maybe 0.5 amperes or even less than that.
So there must be some communication between the mobile as well as the like the charger itself. So, yeah, correct.
So, sir, I have one more question. I just share that is not from this discussion, but related to converters only. Just I share one screen. It's okay. So, sir, this screen is visible. Is
Yes.
plus buck converter.
Yes.
Okay. So, sir, normally, like normal converter is there where when we use only diode, right? In synchronous, so whenever there is like switch is off, then this diode will get forward bias and current will be flowing through this diode normally. But this synchronous buck convert, in synchronous buck converter, we use this switch so that this whatever drop is appearing across this diode, that will not be there because switch is there. So losses in switches. Now, sir, my question is that like if I see this anti-parallel diode and switch, the switch will carry current from top to bottom, right? Then how does it turns on? Because anyway, current will flow in inductor, like due to inductor from bottom to up only. But switch does not allow. Then how this switch gets or carries the current, or like how?
Oh, charge. Okay. Let me actually, there is a conceptual problem. I have to, let me just open my, like, how does the power MOSFET work? I have to just show you. Just give me 1 second. Just 1 second. So, okay. So let me share my screen.
I have to stop. I think what screen can this?
You can, I understood your question. You can stop it. I can share it.
Okay, sir.
See, your major concern is that how is the current flowing from bottom to top or something like that, right?
Yes.
See, okay, so if you look at, this is how a MOSFET looks like. This is a signal MOSFET, this is a power MOSFET, okay? So the difference between a signal MOSFET and a power MOSFET is that this N minus region is there, so the voltage rating is a little bit high. All right, let me see if I can annotate this thing. Right. So what happens is that, let's say you basically in your buck converter, so you don't know how to change the color. Red color. Just give me one. Just give me 1 second. I need to draw it on top. See this one. So now, right? So there is a MOSFET here. And then there is another MOSFET here. So your question is that, that there is an inductor, so there is a current here. So how is the current flowing like this, right? That is the question, right?
True.
So let's just draw this picture. This picture, the source is grounded, and then we actually apply a voltage, some 5 volt or something, so that the channel is basically formed, right? So there is a channel that will be formed. I'll just put it in a different color. The channel I'll put in a different color here. All right, and then the drain is connected to some inductor, right? Okay, this is the scenario, yes. Right? So now, yes. If you think about it, now the channel is formed. Channel is like a wire. Does it matter whether the current is flowing? Does it matter whether the?
So then, what is the use of diode? Then diode need not to be there in anti-parallel.
Diode need not be there. Actually, diode is inherent. Inherent diode. Diode is actually inherent. Diode doesn't matter. Actually, diode is not required. Diode is actually inherent in this kind of thing. Like this is the diode. It's inherent. It is, you don't have to do anything. The diode is there. Diode is generally not put, but there is a requirement for that diode. The requirement is that annotate tool is very, very bad. The requirement is that there is a top FET and there is a bottom FET. So there cannot, these two switches cannot be on at the same time. So when you switch it off, there is a period that will be called the dead time. So during this dead time, for a very small time, this diode will actually has to carry the current. Okay. So during this dead time, this diode will actually carry the current, and then the switch will be turned on. But when the switch is turned on, then the current can flow in both directions. It can flow like this as well as like this. Did I answer your question?
Sir, if let's say purpose of diode is that one only, then switch itself is a bidirectional. Without diode, it means.
But
it
you,
can
see, unless you put a voltage here, the switch will not turn on. But when you put a voltage here, there is a possibility that these two switches can be on at the same time, right? For a very small instant event. Okay, then there will be a short, right? That is why dead time has to be there.
Right, that is okay. But I'm saying if this current can, this MOSFET, the second MOSFET can take current in reverse direction as well. It means this switch itself works as a bidirectional, because
Correct.
D2S it is possible, so S2D also it is taking in this case.
Right, correct. So let's say hypothetically there is no diode. Okay.
Yes, yes.
So now if you turn on this switch was on, then this switch is turned off first, right? So when it is turned off, where will this current go?
This current has to flow through this switch only.
This switch we have not turned it on now, because if you turn it, then there is possibility that there will be a short. Right?
Yes, sir.
Right. So that we have to avoid. That is why dead time has to be there. There will be a very small interval when this switch is also off, this switch is also off. Right. So that is where the diode comes into picture and it carries. It's like a freewheeling diode.
Okay.
Is that okay? Is that right?
Okay, sir. Okay, sir. Thank you, sir. So last question, like in most of the papers, like microgrid or maybe wherever battery is there, do modeling, then they represent this battery with a load. Let's say 12-volt battery is there and the current varies maybe 1 ampere to 2 ampere. Then they say, okay, resistance is varying like 6 ohm to, let's say, 12 ohm. So that way they do modeling, representing battery as a resistance and keeping its load resistance variation 6 ohm to, let's say, 12 ohm in case 1 ampere, 2 ampere. So how far is it correct?
It is not correct. So battery is like, if you, I was just trying to see, I had actually a slide where I can, how do you model a battery? So battery is generally modeled as a voltage source in series with a resistance. That's the simplest model. Okay, in series with a resistance. That resistance is also not fixed. That resistance is dependent on the SOC. All right. So like representing a battery as a resistor is not proper. In fact, it will not even work, because if you think about it, whenever you have a converter with a resistor, initially the voltage across the load is zero. Then the converter starts, right? But if you have a battery, initially the converter voltage is 2 volt. Okay, the battery voltage, right? So therefore, fundamentally they are different actually. So therefore, representing a battery, that is precisely what one of our participants was doing some work on LLC converter. That is what I was telling him also. Okay, you replace your load with a battery, because that is the actual condition, right? So yes,
in most papers, I think they have done like that only, sir.
I say nowadays, nowadays IEEE has gone haywire. I don't know who is. I mean, one joke we will always make is people, even before doing an experiment, plan their paper. See, in our time when I was old, I was younger.
It's a reverse engineering.
We will work for like 3 years and write one transaction. Like in my whole 4 year of my PhD in
please stop recording. Neha, please stop recording. Class is already over.
So at University of Florida, and 4 years I write one transaction paper, because I spent 4 years, and then whatever my finding was, I wrote as a paper. So nowadays, when I see even my students also the same thing. It's the joke is everywhere, that even before planning planning